about my research on the minimum spanning tree. Let's go. Before we get into the minimum spanning tree, we first need to figure out what a spanning tree is. A spanning tree is a subset of a graph, which is, as you can see on the left, it has all the vertices coupled with the minimum possible number of edges. Hence, a spanning tree does not have any cycles and it cannot be disconnected. A minimum spanning tree is a spanning tree that has a minimum weight than all other spanning trees of the same graph. As you can see in the middle, the cost is 11, and on the right, the cost is 7. For data structure, it's all based on the graph. A graph is a common data structure that consists of a finite set of nodes and a set of edges connecting them. There are two kinds of graphs. One is directed graph, where nodes are connected by directed edges and they only go in one direction. Another is undirected graph, where nodes are connected by edges that are bidirectional, as you can see in the picture on the right. There are many algorithms that solve this MST problem, but there are two major ones. The first one is Questle's algorithm. It first sort the graph edges with respect to their weights, and then it starts adding edges to MST from the edges with the smallest weight until the edge of largest weight. And there's one restriction here is that it only adds edges which do not form a cycle, which is the core principle of this spanning tree problem. And second, the prime algorithm, it starts with an empty star tree, a spanning tree. The idea is to maintain two sets of vertices. The first set contains the vertex already included in the MST, and the other contains the vertex not yet included. At every step, it considers all the edges that connect the two sets and picks the minimum weights. After picking the edge, it moves the other endpoint of the edges to the set that contains the MST. And this is the logic that I created to sort of illustrate the backstory behind the logic I was talking about. As you can see, there are like lots of recursive steps in this graph until we find the least cost steps. And this is the pseudocode for both algorithms. The interesting part for the MST is that it actually works a lot in the day-to-day applications. The first one is the network design, which we use it every day, right? So it's like it solves the problem that if you want a set of lines that connect all your offices with a minimum total cost, it should be a spanning tree, especially a minimum spanning tree, since if a network is in a tree, you can always remove some edges and save money. As for the second one, it's the traveling salesperson problem, which is one of the most classical ones. The basic idea was given a list of cities and distance between each pair of cities, what is the shortest possible route that visits each city exactly once and returns to the original city. And the third is quite popular in the business analyst area, which is the cluster analysis. K-clustering problem can be viewed as funding of MST and delete the K+1 most expensive edges. And these are my references for the links that I'm using to during the research. Thank you.